line charge. As I have said, we have dealt in the above discussed with general situations of like what would happen if we have a charge distributed along a line on a service or a volume. Now, we are going to discuss specifically if you have a finite length line that has uniform charge distribution, or an infinite line that has charge distribution. And as you can see on figure 4.6, this is a finite length charge charge distribution. And we are saying that consider a line charge with uniform charge density, rho L. Just a minute, I need to wipe my glasses. Can't see very clearly. So consider a line charge with uniform charge density, rho L, extending from A to B. So you can see A and B along Z axis. So this is Z axis, are shown in figure 4.6. This is our figure 4.6. The charge element dq, this is my charge element dq. It is running, it's considered, sorry, the charge element dq is associated. This is not the whole. This is just the okay, from here to here, that is the line. But the one I have circled is the line element that has charge dq. So notice that clearly without confusion. So in that event, the charge element the line element dl has charge dq, and therefore this charge dq can be found out by multiplying the charge density rho L times the length dl, which gives us dq, as you can see on this equation right there. But then our dl now is pointed towards the z axis. Therefore, we replace the dl with the dz. But now notice very carefully our point of observation, which is this. This is my point x, y, z. My point P described by x, y, and z. So from this diagram, we can see that we are considering a typical illustration in how we can consider this element dl from point P, from the point P, in terms of its dimensions from x, y, and z. So what we have simply done is that we have given that it has the position vector r and the difference between r and, okay, this r and another r prime is simply a vector of how much angle we are making from to the point element dl and to the point B, where is the end of our length L. And the other length that we definitely need to consider is when you move from the origin, which is at 00z, to point A. So I have just probably dwelt there so that you can see that the angles alpha, alpha 1, and alpha 2 that describe the position of B and A and DL, with respect to position P that we are considering. So let that be noted. And therefore, there are some derivations that you are going to be doing, and I'm actually going not to delve much into the derivations. All I will do is to point out the most important aspects. First, if you want to find the total charge due to the line element that is moving from point A from point A to point B, then you can simply do an integral that the charge due to the length is simply the integral of dq, which can be found to be the line charge density, rho L, multiplied with length, which is or elemental length, which is in the z direction. And that will give you the charge that is due to that line element. And that is what this gives us. Of course, our limits of integration move from point A to point B. So, and A and B have their coordinates, and therefore you just replace those and you will get this expression. So there are some mathematical undertakings that you can do here, and by the virtue of the time that we have, I will not delve much, but it is very clear on how each of these steps is done, and where we are heading is equation 420. Equation 420 is now gives us the final solution that you get after you have done the derivation. I was mentioning about alpha 1 and alpha 2 because they will feature prominently in the final equation that defines for you the charge or electric field intensity due to a finite line charge. So we are saying that the electric field intensity, we have skipped the derivations, and all we are saying is that it will be a factor of the line charge density, our normal constant. Remember that we had previously R. R was the distance between the point of observation and the point of the source of the field. So this was our R, but now we are introducing rho to represent this R. So there is nothing that much has changed. What you'll observe here is that we have, in the past we used to have R squared, but now we are simply having rho replacing the R squared. So we are from the derivations, it is clearly that is where the 1R got lost. But we are introducing another concept of a sign of alpha 2 minus sign of alpha 1 in the direction of A rho, and cos alpha 2 minus alpha 1 in the direction of AZ. So this equation, it has denotes the expression of electric field intensity due to a finite line from point A to point B that was described by alpha, as you remember in equation 4.16, alpha 1 and alpha 2, which this was the center, this was alpha, I can't remember which was alpha 2, let me see. Alpha 2 is for B and alpha 1 is for A. So from the point of observation, which is that we were able to get alpha 2 and alpha 1 was bigger, and therefore notice that they come into play there. I'm not going to delve much in how we derive that, but observe this formula. And again, I may not very much require you to remember, because finite line is just a general case. The special case that we normally deal with is infinite line. So what I would actually want you to pay more attention to is infinite line. And if it is an infinite line, the A is at positive infinity and B is at negative infinity, or vice versa. And therefore, our alphas will change from being less than 90 or thereabout to being approaching 90 degrees or pi over 2, and alpha 2 is approaching negative pi over 2. And those are very significant because when you are dealing with cosine, with cosine, this term will get lost because cos of 90 is always 0, be it positive or negative. So this term will get lost in a special case where we have infinite line, and we are going to be left with this term. But again, as I have done very quickly here in the preview of the class, I am just saying that the expression for finite line has minus sine alpha 2 minus sine alpha 1. And since alpha 2 is negative 90 and alpha 1 is positive 90, if you replace that, you actually get negative of negative minus 1 and positive 1, and this gives you a 2. So when you have a 2 and you remember we had a 4 here, it is like we have removed all that. Okay, let me clear my screen and say that after all those derivations, and I think it is important you get, how did I come about? I believe you must have seen the rationale of how we are coming here. All we are saying is that the totality of this term for infinite line gives us a 2. So these 2 cancels, and we end up with electric field intensity due to infinite line is given by the line charge density divided by 2 pi epsilon rho, and rho is the distance between the line, or perpendicular distance. Actually, we have defined that it's the perpendicular distance between the line and the point of observation. So as I believe you can clearly see here that rho is that distance between the line and the point of interest. And A rho is the unit vector along that distance directed from the line charge to the field point. So in very few words, in summary, I'm saying as follows, that if you have a very long line here that has charge density rho L, and you want to observe the electric field at point P, you are simply saying get the elemental length, or get the length perpendicular distance rho, and once you have that, you are going to see that the electric field is going to be given by this formula. So without saying very many words, that summarizes that lengthy derivation. In your own time, you can always try to look at it, but the most important equation that you should remember and should be able to utilize is this one. And engineers, that is what we do. The scholars, like some of us are becoming, we do the rigor or the detailed derivations and show you that the field is going to be given by this. As an engineer, you should do the derivations, yes, but the most important thing as an engineer is to understand the physical meaning of that formula. And the formula that I'm describing to now is that the electric field, due to this long line, is simply going to be given by the formula that is expressed in 4:1. So in a similar manner, we will look at some special charge distributions from a service charge. And before we do that, we are going to review what we already said. We said that consider an infinite sheet of charge in the XY plane with uniform charge density rho S. And then we also said that the charge associated with the elemental area ds can always be expressed as we can see wait, Biri, stop giving him so many stories. Let's keep our chart to bare minimum. Only say the most important things. So we have seen that we have seen how we can derive equation 422. So we now move on to how we can consider an infinite sheet of charge lying on the XY plane. And from equation 412, you can, I'm not going to go through the rigor. Because of the time, I'm not going to go through the derivations. But we are considering this infinite sheet that has a small elemental length 1 and elemental length 2 that are separated by the distance rho and h perpendicular distance to point P of observation. So having said that, you can describe how much electric field strength is experienced at point P due to this charge, due to this sheet that has charge density rho S. Again, avoiding the derivations, which you can always look at, we are coming to a conclusion that says that for an infinite charge, having charge density rho S, the electric field strength E can be expressed simply as equation 426. So that is what we are trying to do, and equation 426 becomes significant for us. And similarly, of course, AN is the unit vector normal to the sheet. And we have surprisingly observed that the electric field strength is independent of the distance between the sheets and the point of observation. That is quite strange. All that matters is the charge density. And what we are saying is that if you have a very long sheet, like I've drawn, very long sheet, and you're observing at point P here, the electric field strength experienced at point P1, let me call it P1, at point P1, and if I observe point P2, this is having radius rho, and this is having, okay, rho 1, and the perpendicular distance from the sheet to point P2 is rho 2. All we are saying is that the distance doesn't matter. All that matters is the service charge density. So that is a very important realization. We don't want to prove that. If you want to prove, you can always do it on your own, which it is properly described in our text. But that is the realization of our regarding an infinite sheet of charge. All right, so our last point we want to discuss is the volume charge. And again, as we saw earlier, we observed that if you have an elemental volume described by dV, having charge density rho v, then the elemental volume will have charge dq equivalent to rho v times dv. Now, we are considering figure 4.8, which is right here. And we want to observe what is the electric field at a point along the z axis due to this volume. So we start with the elemental volume and then consider the entire volume, which is a sphere. And again, it's a bit detailed description of the derivation that comes about. And it's a bit lengthy. If we spend our time doing that, it will take a while. But all we will observe is that the charge density I think we will start with the equation 4.3. The charge density, or the electric field strength due to a volume at point P here, we want to observe E due to this volume. We are saying it will be dependent on the distance Z from the center of that volume to the point of interest. So this is Z. And what we are also observing is that it will no longer be dependent purely on the charge density rho v, but rather on charge itself, because the bigger the volume, the bigger the charge. Therefore, we are going to consider rho v times v to give us Q. Then we are going to say the total charge that is occupied by this volume is the primary factor that determines how much electric field strength is observed at a point P, and the distance of observation comes into play. So the equation that we need to work with is that one. And of course, we are observing at a perpendicular distance from the point of observation to the center of the volume. And if you are now talking about a general volume, you always say the center of the volume, the distance between the center of volume to the point of observation is now defined by R, and the direction of electric field will be AR. So if you now change that you want to observe it at this point, you say R is going to be from the center to a point of observation P2 now, and our unit vector becomes AR, and our length is. Therefore, this is a very important formula that someone must understand. So, in summary, we have expressed finite volume, and what we are saying is that you cannot have an infinite volume. You may have, but in a real scenario, you only have finite volume. But the one that might that considers an infinite case is the infinite area. So if you cannot define an infinite or a finite volume, then an infinite area comes into play. And you're saying that we rarely deal with the finite length, but we often deal with infinite length. So we have gone through the three continuous distributions that are very significant in terms of how you can determine the force due to either or the electric field strength due to either. And that marks the end of the lecture. Let me ask if there is any question or comment. I will, while we wait for that, I will launch a poll. I hope people have understood a little bit today or much today. Please respond on the poll that I am sending